arc length. All right, here we go. So, first of all, what is arc length? I have a graph of a function. Ignore these red triangles for now. The arc length, roughly speaking, it's like the length of the curve. Maybe more precisely, if I took a string and I perfectly laid the string down so that it perfectly matched this curve, and then I pulled the string straight tight and measured how long it is, that's what we're talking about. That's the arc length of the curve. And I'm going to derive a formula for it for you, and that's what these red triangles are about. So how do we do things? How do we approximate stuff with integrals? Well, I take the thing that I'm trying to estimate, I break it up into a bunch of little pieces, I find whatever I'm looking for. In this case, it would be the length of each little piece. I add up all the lengths of all the little pieces, and that's my approximation. And then I do the limit as the number of pieces goes to infinity, and my pieces get smaller and smaller. That's what we're about to do, and that's what these red triangles are about. So if I'm interested in the arc length from A to B, I am going to call A is going to be my x0, and then there's going to be a bunch of like x1, x2, and B is going to be xn, and these are like my subintervals. Now, I want to find the length, or estimate the length for each subinterval. And so here's my first subinterval from x0 to x1. And I'm going to act like this is just a straight line. Of course, I'm doing this curve, but I'm going to approximate it by just doing a straight line. And in the end, this is not going to be too bad because I'm going to do the limit as n goes to infinity, so these pieces are going to get smaller and smaller. And if I look at very short subintervals, the curve is almost a straight line. So this shouldn't be a bad approximation. Now, so I'm going to estimate, because what I'm interested in is the hypotenuse of this right triangle. That's the straight line that I'm using to approximate the length of this curve. And this is the gap in between two of these x values. This is the length of a subinterval. So I'm going to call this delta x sub I. That's just x1 minus x0. This is the difference between these two y values. So if I call this like y0 and this y1, I can call this delta y, whoops, I call this delta x sub I. I should call this delta x sub 1. And I'll call this delta y sub 1. Because these are going to be different. Like when I look at the second subinterval, this is like delta x2. And usually we choose all of our delta x's to be the same. But not all the delta y's are going to be the same. Like this delta y is definitely looks smaller in the picture than this delta y. So this is delta y2. And you can imagine I draw little triangles for all of my subintervals. And of course, if this is delta x1 and this is delta y1, then hopefully I don't mess up the picture too bad, but the hypotenuse would be the square root of delta x1 squared plus delta y1 squared. And similarly, this hypotenuse would be the square root of delta x2 squared plus delta y2 squared. So what I get, if I add up all those hypotenuses, is the sum from I equals 1 to n of delta xi squared plus delta yi squared. And this, you should know what's coming. I just wrote this sum, and now I'm going to talk about the limit as these values of x get closer and closer. So let me do a simple algebra trick. I'm going to pull out the delta xi squared. And when I pull it outside of the square root, it just turns into delta xi. And I'm actually going to write it all the way to the right. So if I pulled that out, of course, this is just a 1 now. And if I pull out, then this becomes like delta yi squared over delta xi squared. So I've got that. And now, as I talk about doing the limit as these values of x get closer and closer, this is basically, here's what I'll do. Not going to be much happening because the top is squared and the bottom is squared. I can just write this delta yi over delta xi. Yeah, I just wanted to see it this way because this here is a slope. In particular, like if I was 1, I would get delta y1 over delta x1, which is the slope of this line segment. It's rise over run. So this is just the slope of the ith line segment. And what do we get if we take the slope and we move these values of x closer and closer? The slope is a derivative. So now I'm just going to tell you the formula. I've got a function and I'm multiplying it by delta xi, and we've done things like this before. This function, this thing we just said is like a slope, which is like a derivative, so that's like f prime of x, and I'm squaring it. And then the delta xi becomes a dx when I transform this into an integral. And the integral, like the limits of integration, should be x equals a and x equals b. And that's the formula we're going to use. If you got a little bit lost, don't worry. We're just going to use this formula. Okay, let's use it for something. Let's find the arc length of some particular function over some interval. Set it up. Integrate from 0 to 1. Using this formula, so I've got a big square root. I go 1 plus, okay. I'm going to fill in this blank with the derivative. So the derivative would be 2/3 times 3/2 x to the 1/2, right? I just brought the 3/2 down and decreased it by 1. Of course, that goes away. And I chose an easy one for our first example. In particular, when I take x to the 1/2 and I square it, that's just x. And this is an easy antiderivative to do. Like if this was just square root of x, well, okay, here's what I'll do. It's a 1/2 power, of course. If this was just x to the 1/2, then I would do the normal power rule. But this is, what I'm going to do is I'm going to skip the work of an easy substitution again. You can do w equals 1 plus x if you like, but I'm going to skip the work. This would turn into 1 plus x to the 3/2 with a 2/3 in front. 0 to 1. now we're on the home stretch. 2/3. Now I've got a 2 to the 3/2 minus 1 to the 3/2, which is just 1. And why don't we just put a box on that and call that our answer? Okay. So we just have this formula and we use it. Of course, what can make these examples hard is you might find something that's hard to integrate, and we didn't really run into too much trouble on this first example, but crazy things can pop up. Let's do another one. So I've got this function, integral from 0 to 1. So here we go. I'm doing this formula, so it's 1 plus the derivative squared. I'm going to fill that blank in with whatever the derivative is. Okay, what's the derivative? Well, this is just e to the x plus 1/4. And then this, for this I need the chain rule, so this is like e to the negative x times the derivative of the inside, which is -1. Okay. So what happens here? All right. So I am really not going to do too much in this step. -1/4 e to the minus x. Okay, I barely did anything. We want to square this out because we have kind of an algebraic mess to deal with here. How does this go? I'm going to have my first thing squared, so that's e to the 2x. And then I have 2 times this, so that's 2 e to the x times -1/4 e to the negative x. Yeah, just so everybody follows me. I'm just using this. And while I'm at it, let me also... a minus b squared is so similar, but I'll write that as well. Okay, so what we're missing is this squared. 1/16 e to the negative 2x. Okay, so that just happened, and why did I do that? It seems that my life just got worse, but wait. Let's look at this thing in the middle. First of all, those just cancel each other. Those are reciprocals. So let me clean it up. Not a lot's going to happen. This is -1/2. Okay, now another step where not a lot's going to happen. Eventually something's going to happen, but I've got a 1 and a -1/2. I can combine those. So those are going to make a +1/2, and I'm going to put the +1/2 right where this -1/2 is, and the 1's going to be gone. So e to the 2x plus 1/2 plus 1/16 e to the -2x dx. Okay, now here's the thing that's going to save us, because this still looks horrible. I've got e to the 2x, I've got e to the -2x, it's all underneath the square root. I don't like the looks of this at all, but I know what's going to happen. The thing underneath the square root is actually a perfect square. And I can recognize that this is something that's very particular to arc length and also surface area. We're going to cover surface area next, and it's a similar formula, and that's why similar things come up. But this is a very particular phenomenon for these types of integrals. I can tell you this is going to be e to the x plus 1/4 e to the negative x squared. Now, how do I know that? It's related to this information. So there's a couple of things to notice about what just happened. Like I had, at some point, I had this. I squared this out, and this is like a minus b squared. I squared this out, and the thing in the middle was a minus a half. And I combined it with this 1, and it turned into a plus a half. But look, a minus b squared and a plus b squared are almost the same thing except for the middle. The only difference is that the middle, this one has a plus and this one has a minus. So if when I square this out, it has a minus a half in the middle, and then I change that minus a half to a plus a half in the middle, then instead of being a minus b squared, it's now a plus b squared. So instead of being like this, a minus b squared, it's now like this, a plus b squared. All that's different is that this was a minus and now it's a plus. We can check it, like we can imagine squaring this out and getting this. Of course, like I would do the first thing squared, that's e to the 2x. I would do 2 times this, and the e to the x and the e to the minus x cancel, and 2 times a fourth is a half. And then I would have this squared, which is this. So everything checks out. This is the same thing. It can be very difficult to recognize if you're not looking for it, but you should be looking for this with arc length. In fact, I think it's safe to say that probably most of the arc length examples you're ever going to do have this going on. Anyway, now it's like a miracle. This is squared and I've got a square root, so that just goes away. So where am I at now? I've just got e to the x plus 1/4 e to the minus x. Antiderivative of e to the x is e to the x. 1/4 carries through. The antiderivative of e to the negative x is just like this, except there should be a -1 to deal with this negative x. 0 to 1, and we'll plug it in and we'll be good. So I've got e minus 1/4 e to the -1, and then I'm going to subtract, well, e to the 0 is 1, so this is 1 minus 1/4. So e minus 1/4 e to the -1 minus 3/4. And there we have it.